Welcome to topic 2 of statistics and experimental design. Last week we had a look at an introduction to the subject, as well as looking at some nomenclature that we use commonly in sampling and experimental design, including the difference between a population and a sample, for example. As well as we moved into our first numerical descriptors of data, including the mean, the standard deviation, and the median. And this week we look at some visual mechanisms, or we start looking at some visual mechanisms for describing and summarizing data. And at the end, we look at a different way of demonstrating spread. In the first topic, we looked at the use of the standard deviation as a way of displaying or summarizing the spread in our data set. The standard deviation works very well when we are using the mean, so it's used alongside the mean, but it isn't appropriate for use with the median. And we saw that the median was an appropriate mechanism for describing the center of a data set, and it is the definition of the center of a data set. And so we need a way that we can quickly summarize the spread around this median in those particular data sets appropriate for the median, which are those skewed data sets. And we saw the Shelbyville house price data set as an example of that, where most house prices were in the $300,000 range, and there were some, only a couple, around $700,000 and $800,000, and they skewed the data set in one direction. And that's why we use the median a lot of the time for house prices. So we'll end this topic looking at a way that we can represent the spread for these skewed data sets. One way that we do show or summarize data visually is via a histogram, and that's really the go-to visualization tool. We'll be looking at a couple of others, some which are used for categorical data sets and some which are used for numerical data sets. And we'll mostly be looking at ways to visualize numerical data from here on out. But the histogram is the go-to mechanism, and we introduced it in topic 1. And we have one here on the first slide. On the x-axis, we have ranges of data, attributes of a variable, and on the y-axis we have the count. So the number of times that value for that variable is found in our data set. And here we have an obscure data set, deaths by horse kick in the Prussian Cavalry Corps between 1875 and 1894. And you can see that 3 to 4 deaths per year occurred in 2 years. Moving along, 5 to 6 deaths occurred 4 years. In 4 years between that period. And in this data set we have a number of peaks. We'll be describing how we can interpret the peaks in our histogram to help us understand our data set a little bit better. So this is one example of a histogram. We'll be looking at many more, and you'll be generating some as well. There are 3 data sets for you to download at the beginning of this talk, and we'll see that on the next slide, and we'll be working through those as we go. So here's that flowchart summarizing the different types of variables again, with numerical / quantitative on the left and categorical / qualitative on the right. And both these types of variables have methods for summarizing them visually. There's graphical means and numerical means. Numerical, we've seen. With categorical data, we have to use proportions or counts. With numerical data, we have a lot more options, including the mean and the median, as we saw, standard deviation, and we'll be looking at ways to summarize the spread of skewed data, where we use the median a bit later on in this topic. But we're going to start off looking at graphical or visual means. With numerical data, we'll be looking primarily at histograms and dot plots. There's also stem and leaf plots as well. We won't be examining those here. We'll be concentrating on histograms and dot plots, and one other as well, box plots, which are very popular in scientific literature. We'll start off by looking at graphical means for summarising categorical data using bar graphs and pie charts. They're very simple, and I think they're probably where a lot of people start with their Excel graphing skills, the bar graph and the pie chart. So we'll just be reflecting on those a little bit, reminding ourselves on how to do them in Excel as well as Minitab before moving into the numerical sphere. So I've provided you with 3 data sets, one which has the mean maximum temperature for every month since 1855 for the Melbourne weather station on the corner of Latrobe Street and Victoria Road, in Celsius. The Inglis bloodstock sales results for, I think it was June last year, for fillies. So that's an auction for potential racehorses, and it provides a whole lot of information about the horse and the price they sold for at auction. And then finally there's one for the Yarra River and the height of the river at 2 measuring stations in Templestowe and Warrandyte. When you have a look at them, you can download them all from the datasets folder, and they're there for you to practice some of the concepts that we looked at last week, as well as looking at this week, and we're probably going back to them in future weeks as well. All the techniques you're required to use with them are found either within the notes in those slides that give you Excel techniques, as well as a self-guided lesson in topic 2 on semi-advanced Excel skills. It's important to look at that self-guided lesson if you aren't advanced at Excel, because each of these data sets has been chosen deliberately or collated deliberately such that they require filtering. They're not, for example, the Yarra Streamflow, which has Warrandyte and Templestowe streamflow data. There's not just a nice set of columns with the Warrandyte data and a nice set with the Templestowe data. They're all mixed up within themselves, between themselves, as most data is presented to you when you retrieve data loggers from the field or you download it from the Bureau of Meteorology. You often get these complex data sets that need some level of data extraction before it's even analysed. So some of the techniques I explore in that self-guided lesson allows you to pull out particular aspects of a large data set for it to be analysed separately. We'll be using filter functions, subtotaling functions, average if, as well as eventually producing histograms based on this data later in this lesson. I provided for you, along with the self-guided lesson, which has screenshots and goes quite slowly, a narrated video of me bumbling through the Melbourne maximum temperature data set and getting the mean and standard deviation. And it's probably a good idea at this point even to stop or pause this slideshow, download those 3 data sets, and have a go at getting the mean maximum temperature in May and January, which reminds me that I did May and June in the video, but do it for May and January or May and June, it's fine. Get the mean and standard deviation for bay, brown, chestnut and grey fillies from the Inglis bloodstock sales. Bay fillies are given the colour B dot, brown are given BR dot, chestnuts CH dot, and grey fillies are GR dot. That's the abbreviation for the colours. And the stream flows are broken into Warrandyte and Templestowe. So these are all, you can see, categorical variables which will be analysing numerical data based on them. in those data sets. So when you download those, have a quick look at them, have a squiz, see how they're built, and maybe watch the video and do the self-guided lesson at this point, even just to allow you to calculate the mean and standard deviation for those variables that I've listed there. And then, as I said, later on we'll be doing histograms based on this data and seeing whether or not they're skewed, and if they are skewed, what summary statistics are we going to use to represent them. So looking at categorical data now and how to present it in a visual form with graphs, which can be figures in your reports now and going forward in the future. Sorry to use the term going forward. From topic 1, we discussed that categorical data can only be expressed in counts, so how many of each fall within those categorical variables, or proportions, so what proportion do they make up of the whole. And subsequently, we generally only represent categorical data using bar graphs or pie charts. Confusingly, as I also discussed, often we use categorical variables as a way of extracting numerical data from larger data sets and analysing that. So for example, in the Melbourne Cup winners data set, which could be broken into winning horses that were stallions, winning ones that were geldings, and winning ones which were mares, we could then do analysis on, say, the performance of just the stallions. So what was the mean winning time of stallions? So we're doing analysis on numerical data, but we've divided the numerical data up according to particular categorical variables, being the sex or type of horse. Bar graphs should be quite familiar to you, and this in a way represents a histogram, but on the x-axis we have the categorical variable, and on the y-axis we have the count or proportion based on that categorical variable. In this case I've put counts, so the number of wins that each of these categorical variables have had in the Melbourne Cup: horses or stallions, geldings and mares. Generally the order of the bars in these bar graphs can be presented arbitrarily. However, it's best to order them for maximum effect. So if you're presenting results and then discussing them, and maybe in this case you might be discussing the fact that stallions, there's been more stallion winners than gelding winners, then you'd probably present those two bars next to each other on the graph. Using Excel, creating bar graphs couldn't be easier. Just summarize or just organize your data into columns using consistent categorical variables. Summarize the data for each variable with the function equals countif. Put in the array of cells that we're counting, and then equals quotation marks equals the name of whatever that categorical variable is, end quotation marks, and that will count the number of instances of that categorical variable. Try that out with the Melbourne Cup winners to make these summary tables based on count if. So you'd go count if, put the array, comma, which would be all the winners, comma, quotation marks, equals whatever the abbreviation for that particular gender of horse is, close quotation marks, close bracket, press enter, got your count if. Put your count ifs in a nice little column, then go simply highlight them, insert chart, and select a clustered column. There is an example video demonstrating this, as well as how to label the axes. Using Minitab, it's a lot easier than with Excel. You simply put your data into columns, as with Excel. Go to the graph menu, select bar chart, and then you actually tell Minitab what you want to put in the bars, and in this case counts of unique variables, and it'll automatically go through, find each of the unique categorical variables and count them, and then derive a bar graph for you for it. Simple. Pie chart is derived very much in the same way as a bar graph, using counts. I'll show you how to do it in Excel and Minitab. It's very easy. They're not often used, the pie chart, in scientific publications, but they're often used in prospectuses and for reports for management, because it allows you to quite effectively show things that are quite powerful. For example, how one certain categorical variable is overrepresented compared to the other ones. It's particularly effective for categorical variables which are extremely poorly represented, so they represent a very small piece of pie. So I should say a pie chart, if you're not familiar with them, what it does is convert your data into proportions as shown as a slice of pie. So here, for example, the horses are given around 60% of the pie. That's because they represent 60% of the winners of the Melbourne Cup. Mares are only about 8%, so they're given the 8% of the pie, or this clock face, if you like. Often there's a temptation to produce 3D versions of these. Don't do that. It doesn't add any extra information to them. But as I said, these are often used for more general publications and not for scientific publications. So in the following two slides, you'll see that the creation of pie charts is very similar to the creation of a bar graph, except you select pie rather than bar graph. So we move on now to visualization methods for numerical data. We've looked at two simple methods for visualizing summaries of categorical data. Now we'll look at dot plots, histograms, and box plots. And the first one we'll look at is probably the crudest, I suppose, method, but it's also can be one of the more helpful ones, especially for on-the-spot visualizations. These are dot plots. And all we simply do is, well, really it's a variant on the bar graph we saw before. It's also a variant on histograms. We present the full range of possible values on the x-axis for a particular variable. Here we have, quite obscurely, the healing rates of anaesthetized newts, measured in micrometers per hour. And so you represent the full breadth of values possible for that categorical variable, or realistic for that categorical variable with the data set that you have. And then you simply put a dot above the point where a value appears. So using this example of the anaesthetized newts, one newt healed at 11 micrometers per hour, so a dot was placed above the 11. There was one at 12, so it was placed above the 12. Wherever there's two values at the same point, then they're just stacked on top of each other. Where's one? There's 22 and 23 micrometers per hour. There were two newts at each at those levels, and so two dots were put on top of each other. This allows us to very quickly visualize spread and the distribution of data and see extreme values which are far away from the group. And we call these values outliers, and we'll look at a technical way of calculating actual outliers, not just visual ones. But here it's suggested that maybe this value at 40 might be an outlier, an extreme value that isn't representative of the normal range, because it's 5 micrometers per hour away from its nearest other value, whereas no other values are isolated by themselves to that extreme. These are really handy dot plots. They can be done on the forklift, they can be done out in the field. You can quickly do them on the back of an envelope to get a gauge of the distribution of data in real time. Now, building towards our discussion of histograms, and again we've encountered histograms already in this subject, this being only topic 2. But whereas dot plots that we saw just before had every number in the x-axis, histograms have number ranges. So let's think back to that Shelbyville data set. The bars in that, the histogram produced from that, were the counts for houses that fell within a range of house prices. So $250,000 to $300,000. How many fell within that bracket? $300,000 to $350,000. How many fell within that bracket? We can see this type of technique used in frequency distribution tables, which I've produced here for you from an example data set. So we have an example data set ranging from 12 to 58, and in a table I've counted the number of points that fell between ranges of 10. So 10 from 10 to 20, 20 to 30, 30 to 40. How many fall within each of those bands? Just put that in frequency. That could also be titled count. And then they've just been converted into the relative frequency. So 3 divided by 20 is 0.15. The relative frequencies have to add up to 1, of course, and then those relative frequencies are being converted into percentages by multiplying by 100. So here we're using ranges and counting the number of data points that fall within the ranges, and this is exactly all that histograms do. Instead of presenting it in a table like this, histograms present it graphically. In Excel terms, these classes or ranges, as in 10 to 20, 20 to 30, are referred to as bins, but the concept is exactly the same. A bin, B-I-N. So here's our histogram again. As I said, in the x-axis we have ranges rather than absolute numbers, and in the y-axis we have the frequency or count of data points that fall within those ranges. In the example one presented here, the numbers in the x-axis there are just the center point of each of the ranges. So that first range there would be 0 to 10 with 5 in the middle. The next one 10 to 20. So there's no data points that fall between 0 and 10, but there's 3 that fall between 0 and 20 and 6 between 20 and 30. We'll be concentrating on histograms quite a lot in this topic and the next, or the next time we look at numerical data. And what we'll particularly be looking at is trend lines which are generated using histograms. We'll see those in the next couple of slides. And we'll be looking at whether or not we can tell if the histogram's skewed left or right, or if it's an even distribution of the histogram. Questions often asked, what ranges do we put in the x-axis? Well, there's no perfect solution to that. If we make the ranges too large, then often the histogram doesn't have enough resolution to allow us to see any patterns in the data. And if it's too detailed, it's not summarized enough, and the actual pattern gets clouded by this sort of confused Manhattan of peaks. So let's have a look at a few histograms that give us a good example of this. Here we have a range of histograms generated from the same data set but using different ranges in the x-axis. The data set in this case was a whole flock of toucans that had their beaks measured and recorded, and then a histogram generated to look at the frequency of different beak lengths in that flock. Starting in the top left, we have very small ranges where counts were made, And you can see that the distribution becomes quite confused. There's peaks and then there's troughs, peaks and troughs. So it's a little harder to see general patterns. And the next one to the right of that, so the top right, the ranges become smaller. So let's have a look in that first top left. They've done counts on beak lengths in 0.1 increments. So 0.1? No, 0.05 centimetre increments. In the next one they've used 0.1, so they've doubled the size of the ranges. For example, how many toucans had a beak length between 2.5 and 2.6, whereas in the first histogram it was how many between 2.5 and 2.55. You can see in the top right one it's summarised a bit more, and those peaks and troughs have been evened out a little bit, but they're still there. But now we move into the bottom left and bottom right one, surrounded by this bold box. And you can see that the distribution is clear to see. In the bottom left, now the ranges are 0.25 centimetres in size, so counting the number of beaks between 2.5 and 2.75. And in the bottom right, which is probably a little too summarised, the ranges are 0.5. And then the far bottom right, the ranges are about 0.7, and that's far too summarised. It's hard to get the pattern in the beak lengths with that. So I'd say probably the optimal one there is that bottom left one with the beak size between 0.25. The beauty of generating histograms with software is that we can alter the ranges in that x-axis, the bin sizes in Excel speak, to get the perfect histogram. In fact, Excel and Minitab will choose bin ranges for us if we don't offer up our own guidance for those programs. So imagine now that I drew a line that followed along the peaks of those bars from the lowest up to the highest and back down again, and followed along that histogram. If we had an even distribution where the highest frequency occurrences were in the middle and then they petered out either side, so for example most toucan beak lengths were in the middle, sort of a medium length, then we'd get this pattern here. We'd get this nice smooth curve up, peaking in the middle and then going back down again, in which case the mean and the median of this data set would be pretty similar to each other. If on the other hand most of the values are on the higher end of the scale and few on the lower end, so most toucan beaks were quite long and there was only a few that were short, then we'd get this skewed data set here. This is actually referred to as a left skewed histogram, which can be counterintuitive a little bit, but makes sense. The left skewed represents where the tail of it is, and the hump is the body of the histogram. In these cases, the median is larger than the mean. The alternative to this is where we have a lot of smaller values and only a few larger values, and we get the hump on the left and we get the skew to the right. These are right skewed histograms. A classic example of this would be the Shelbyville data set, where we had a lot of low valued housing and very low amount of high value housing. That was a right skewed histogram. In these cases, the median will be lower than the mean. And I think also you can see from this that the median is probably more representative than the mean for these data sets, and the same for the left skewed histogram as well. In which case we can see just from these two examples that the median is generally the best tool for measuring this, well, summarizing the center of a data set in skewed distributions. Let's look at a real example now. Here we have a histogram of the winning times of the Melbourne Cup for all years, from the very first data point, 1861, up until the most recent winner. I've generated this, so we've got the winning time in seconds on the x-axis, and we have the number of winners within those ranges on the y-axis. And so our ranges here are, what, 0.4 seconds apart. So we've got 3.16 to 3.2. Again, the number at the bottom there is representing the middle of the distribution of the range, and then 3.2 to 3.24. This looks like a right skewed distribution to me. We'll have a look on the next slide to see if we draw a line over it, if we can visualize that skew. And yes, I've got Excel to draw a trend line over the top to follow as best as possible the peaks of this histogram. And yes, you can see quite clearly that there is a right skew in this data. So there's most horses won between 3.2 and 3.32 seconds, and a few won in much higher times, up to around 3.54 and even beyond that as well. So this is a classic right skew distribution, and would be similar to that Shelbyville example as well. Now we'll see how we visualize this skew, and then we can use this histogram to try and piece out where this spread comes from, so we can actually draw some conclusions from the data quite simply. So what I've done is I was remembering back to when we did the mean and standard deviation of this data set, and I thought, alright, let's try and piece out where this skew is coming from. What would happen if I removed the mares from the data set, as well as focused on only the most recent half of the winners, so the winners from 1941 to today? So I filtered the data set for winners since 1941 and only male or horse and gelding winners, and the skew did reduce. You can see that here, that there's less of that right skew there, less of that pronounced tail. So that was a guess based on the mean and standard deviation we did before, but you could get this through trial and error by doing histograms of different elements of the data and seeing how the histogram changes when you modify it for different categorical variables. When I place the mean winning time for mares and stallions, and then the mean winning time before 1941 and post 1941 over that original histogram using all data, you can see how this skew might emerge. Remember, it was a right skew, or you can see it here, it's a right hand skew. And I got rid of a lot of that right skew by removing the mares and removing the first half of the winners, so the old times. Both the mares and the winners before 1941 both have a mean winning time which is larger than the mean winning time for stallions and those winners after 1941. So you can see that how that would have pushed the distribution to the right. So we've looked at some histograms which show some skew, and we've seen how the mean for skewed data sets doesn't give us the best representation often. They're best used for the even data sets where the peak is right in the middle of the distribution. And with the mean, we couple it with a standard deviation to show spread. But what do we show for skewed data sets when we're using the median? Because we can't use the standard deviation for that, because the standard deviation is derived from the mean. So in place of the standard deviation and the mean, we present the 5-number summary, often for skewed data sets. The 5-number summary is very simple. First of all, it contains the minimum number and the maximum number, XL and XM. It contains the median, which we call Q2, and it has the first quartile and the third quartile. The first quartile is the number which represents the bottom 25% of the distribution. In other words, 25% of the numbers are less than that number. The third quartile is the 75% mark. 75% of numbers are less than that number, and 25% of the data points are greater. Quartiles are just versions of percentiles, and the percentile is a value, as I said before, which is a percentage of a distance along an ordered array of numbers. So the 50th percentile would be 50% of the way along the ordered array of numbers. Here we have an ordered array of numbers, in this case exam scores, ranging from 38 to 90. So the 50th percentile would be 50% of the way along that array, halfway along, so 50% are less and 50% are higher. In other words, that's the median. So the median is actually the 50th percentile. In this case, it's 66. The 10th percentile is simply would be 10% of the numbers are below it and 90% are above it. In this case, there's 20 numbers in this sample. 10% of 20 is 2, so the 10th percentile would be the second score along the array, 43. So 10% of exam scores are 43 or less, and 90% are greater than 43. You most often hear exam scores talked about in the upper something percentile. So the upper 10th percentile, that's the reverse of normal percentiles. So the upper 10th percentile would actually be the 90th percentile, where 90% of the scores are less than that and 10% are above it. The quartiles are simply the 25th and the 75th percentiles. So here's the full 5-number summary for this data set, maximum being 90%, maximum the exam score was 90, the minimum 38, the median is 66, the 25th percentile or the first quartile was 50, so 25% of people scored 50 or less, so in other words about 75% of the class passed, and the third quartile or the 75th percentile was 80%, so 25% of the class got above 80. Now we can use this to calculate the true version of the standard deviation for the median, and that is the interquartile range. And so this is what's quoted along with the median often. And the interquartile range is simply the third quartile minus the first quartile. Q3 minus Q1. Another benefit of this interquartile range is it allows us to formally define an outlier, an extreme value which is not like the other values in the distribution. And we define those as lower and upper outliers, so extremely low values and extremely high values. And they're defined as the first quartile minus 1.5 times the interquartile range. The upper outliers, the third quartile minus 1.5 times the interquartile range. This brings us to our final visualization tool for this topic, box plots. And box plots are just used to visually show the 5-number summary. Here we have one running horizontally with an x-axis. There's no y-axis for these, just the x-axis. And on the x-axis we have the full range of numbers. And we have a line, we rule a line from the minimum number to the maximum number, xs or xm through to xl. We put a dot on either end. Then we put a dot at the Q1 point, dot at the median, and a dot at the third quartile. And then we draw a rectangle running from the first quartile to the third quartile as demonstrated here, with a line marking the median. This is a box plot, so there's the box is that rectangle in the middle with the lines jutting out either side showing the full range of data. We'll see how these are fantastic for visualizing skew. Here's another box plot, this one running vertically, and they can be represented either way. We just have the categorical variable listed to label the box plot there on the x-axis. And the y-axis, again, we have the range of data, and this is for the data set there listed on the left. And again, we have the minimum value there, the maximum with this box, or these two rectangles joined together, showing where the first quartile is the median and the third quartile. Here we see that box plots can be just as effective as histograms in showing skew, except that the box plots have the added advantage of showing the viewer immediately where the median and the quartiles are in the range. And here finally is the representation of left and right skewed box plots with an even distribution, here referred to as symmetric, but we'll refer to them as even distribution in the middle. Of note as well, the benefit of the box plot is it gives very quickly shows you the interquartile range. Interquartile range showing the spread, the average spread of the data, the version of the standard deviation for the median. And that middle symmetric, or what we call an even distribution, the spread is very small. It's a very tight data set. That box is very small. The range is quite large, but the box in the middle is very small. The left skewed and the right skewed data, on the other hand, have a large interquartile range, Q3 minus Q1, large distance between those quartiles, which shows that a lot of the data is very well spread. Well, not well spread, but is very spread. So what I want you to do following this topic here is go to those data sets that we talk about right at the start of the topic and develop a box plot using Minitab and work out whether or not they're skewed. Use Excel, and there's a video demonstration on how to use Minitab to develop a box plot for those. Work out if any of the horse values would be considered outliers. So go to the bloodstock data set and work out if there's any outliers based on the interquartile range. And you can do that just for, say, the brown fillies. And then produce a histogram, the mean and standard deviation, the median, and the whole 5-number summary for each of those data sets. And again, for each of these requirements, there's a video demonstration on how to do it.